Welcome to the Actionable Futurist podcast, a show all about the near-term future with practical and actionable advice from a range of global experts to help you stay ahead of the curve. Every episode answers the question, what's the future of? With voices and opinions that need to be heard. Your host is international keynote speaker and actionable futurist Andrew Grill.
Today's guest is Richard Hopkins from IBM. He's an IBM Distinguished Engineer and Fellow of the UK's Royal Academy of Engineering and a Fellow of the Institution of Engineering Technology. He was also the 19th President of IBM's Academy of Technology. Richard is dedicated to bringing on the next generation of technical talent as a STEM ambassador and regularly presents to the UK's National Cyber Security Centre's Cyber First program on topics such as artificial intelligence, quantum computing, and the future of technology. In his spare time, he directly inspires kids and keeps up to date with technology. Welcome, Richard.
Thank you, Andrew. Good to see you again.
You too. Look, I'm delighted to have someone from my old company, IBM, back on the show and to speak about a very futuristic concept, that of quantum computing. So for our global audience, could you give us your definition of what quantum computing is?
How long have you got? Quantum computing is one of those things that is a relatively recent phenomenon. In the early 20th century, basically Heisenberg and Bohr and that lot came up with the idea that physics wasn't quite so continuous as we thought, and everything could be divided down into quanta. And they discovered things like the hydrogen lines from excited hydrogen atoms and started formulating a theory of how matter actually worked at the level of the very, very small. And this is kind of all tied in with a scientist called Richard Feynman, who was born about the same time in the 1930s. At this point, he would be taking radios apart and putting them back together again. But basically, that new way of looking at things was completely counterintuitive. It just didn't have a corollary in the real world, and that's quantum mechanics. And then in the 1970s or so, Charles Bennett, who's an IBM fellow, came up with the idea of quantum information theory because, could you start using what we now call qubits, which are bits of information that are stored as quantum bits of information. Could we use those to start actually describing information, how information moves around, how it's stored? And this is kind of a universal way of looking at information, because on computers we use bits and zeros and ones. Qubits use something slightly more sophisticated called qubits. So once you had the idea of a qubit, you then get some Richard Feynman bringing people from all around the world together at an MIT conference in the 1980s, because he was getting very frustrated. He'd been a long-time user of computers. He'd used them for the work that he did on nuclear bombs and everything else. And he was frustrated because he knew by the mathematics and by quantum mechanics that the computers we use today wouldn't be able to simulate or understand nature at that small level. It gets too hard. It gets too messy for the computers to deal with it. It scales exponentially. So he came up with the idea of saying, well, if we really want something to understand nature at that level, what we need is a quantum computer. And of course, then at this MIT conference in the 80s, Charles E. Bennett and Feynman and Deutsch and many others got together and started putting together the fundamentals of what a quantum computer might look like, how in theory it might work. Everybody looked at it and went, that's a really hard problem. That's a really hard engineering problem. Not just a hard maths problem, but engineering, because, to actually manipulate things down at this very small, delicate level is incredibly hard. And then, of course, IBM and others started working on things like scanning tunneling electron microscopes and moving atoms around. So we famously we spelt the IBM logo using atoms. The technology started making it possible to begin to think about building one of these weird quantum machines that might be able to do that. And then a scientist called Shaw came up with an algorithm that basically suggested that we'd be able to look at kind of problems that we couldn't do any other way at a speed that would be unheard of on a conventional computer. And that kind of then drove the investment into the industry, because people will see that this has potential real-world impact, potential real-world capability. And that's where we are today, with scientists and engineers all around the world researching and building quantum computers.
So one thing you said brought back some horrible memories of first-year engineering, Heisenberg. I remember Heisenberg's uncertainty principle. He was related to that in some way, I'm sure. Fourier transform, all those things that I thought I'd never need again, I'm now hearing again. The whole quantum computer, I've never actually seen one up close. I've seen lots of pictures, including you standing in front of one. Just describe to me how they work and some of the physical things you have to do. I understand it has to be a very cold environment, so it's not something I'm going to wear on my wrist, is it?
Not really, no, not yet anyway. I mean, there are lots of different kinds of quantum computers. So IBM is creating superconducting qubit computers that uses the properties of matter when it's very cold to actually enable us to create these really delicate qubits and to manipulate them. So when you look at a quantum computer, at the moment it looks like a very large wardrobe, I guess, and that wardrobe has a big canister in the middle of it, and that canister is essentially a cryogenic chamber. It allows you to cool the actual inside of the quantum computer down. So at the very top of the quantum computer, and these things are about 6 foot tall at the moment, it's about 1 Kelvin. Now, again, you may remember that 1 Kelvin is almost as cold as you can get. Okay, but that's nothing in a quantum computer because that's still quite hot. So by the time you get to the bottom of that cylinder, where the actual chip is for the quantum computer itself, that's at about 13 millikelvin. Okay, so it's incredibly, it's hard to explain how cold it is. It is about 30 times colder than outer space, and that's cold. Okay, and then the whole thing of the quantum computer is how do you get instructions into that chip at the bottom of that well, if you like, and how do you get the answers back again without the whole thing heating up and destroying the coherence of the quantum computer? So what you're trying to do is insulate the whole thing from the real world as much as you can so that the actual quantum qubits can continue to work and do their job as a quantum computer. Most of what you see, which is this kind of beautiful chandelier of layers of gold and wires and things, they're all there to essentially help cool the thing down and to attenuate the signals as they come in and then amplify the signals as they come out so they don't heat the machine up. And then at the back of the machine, in wonderful science fiction gloriousness, you have a whole pile of small computers that are all flashing green lights, which are marvellous, that basically take the programs you write and turn them into microwave pulses and then inject those into the quantum computer, then bring them out the other side. So it's an extraordinary looking thing. It doesn't look like any computer you've ever seen before, and it doesn't work like any computer you've ever seen before either. They are a thing of both beauty and power. They're marvellous.
So this is not something that you can pick up at the local hardware store. And obviously IBM has invested a lot of time and money. And given my time at IBM, the amount of research you do and the research people you have, and you're very experienced. So talk to me about IBM's involvement in this space. When did it start? And where is IBM showing leadership in the quantum computing space?
It started at that very first conference. The conference where Feynman actually said if we want to really understand nature, we're going to need something that works in the same way as nature, which is quantum. That was a joint MIT-IBM conference back in 1981 with the IBM fellow there. So we were there at the start, and we've continued all the way through. We were the people who put the first quantum computer onto the internet, for people to use, onto the cloud, which was unbelievably now back in 2016, which feels like yesterday, but in fact is quite a long time ago now. We've got more quantum computers out there than anybody else. We've got 20 quantum computers on the cloud at the moment for people to use. Some of them free for them to use as well, so we can help build skills and that kind of thing in the area. One of those quantum devices, which is available for our premium customers, is a 127 qubit device, which again is a world-leading number of qubits on a single quantum computer. So we like to think we're pushing the boundaries and we're at the front of those boundaries, and we are pushing hard to get to a position of what we call quantum advantage, which is where a quantum computer will be able to do a real-world, real-life problem that a normal classical computer would never be able to do, and do it more cost-effectively than a normal computer. So, that's kind of where we are. And we've even installed some of those beautiful wardrobe-sized machines in other places around the world. So Germany has got one. Japan's got one. These are at research institutes, so they can do their own deep research onto quantum computers. And we're doing another, 4 or 5 installs of those kind of devices as well. So they're out there in the cloud. You can use them. Anybody can use them. And then there's also dedicated instances, but not compared to the number of computers in the world, not very many, but they are out there. And getting a quantum computer out of the lab itself was a huge undertaking and a huge achievement, I think.
It cast my mind back to the time, and this is probably where we are now, where you actually have to run batches. So the computers are a scarce resource. And I remember back in 1983 using punch cards to write basic programs, send them off to the Angle Park Computing Centre in Adelaide, and a week later I get back my big bit of paper with my Snoopy program or whatever it was. And so back then, we basically had to rent time on what was then a supercomputer. I suppose at the moment what we're seeing is you're allowing people on the internet and also in research areas to basically run batch programs. Is that kind of where we are at the moment? We're back to running this rather than it being real time, but it's in the cloud. You're saying you can actually almost with a credit card rent time on one of your quantum computers.
It still boggles my mind slightly that they are available, first of all. But secondly, that yes, at the moment there's a batch way of getting in. IBM's got a long history in batch. We like batch. But we also like serverless. So, the news that's coming down the tracks is that we're going to move from this kind of batch way of interacting with quantum machines into literally a serverless way of acting with quantum machines. So you'll be able to write programs that run partially on classical computers, partially on quantum computers, and they'll be able to work together, and you'll be able to call on that capabilities in a much more online kind of way. And then certain of those capabilities and libraries will become, APIs and capabilities you can call in a serverless way. So basically, we're moving already, in the space of 6 years or so, from a batch orientation to an online to a serverless, and we're doing that transition over the next year or so. So it's moving quickly. It is definitely moving quickly. And coming back to your punch cards. Punch cards are almost exactly contemporaneous with quantum technology. So they were invented about 1913 as well. 80-column punch cards with the squares. That was the IBM punch card standard that lasted almost forever. That was invented about the same time as the quantum theory that we're now talking about as a computer paradigm was invented too.
Absolutely amazing history there and how things have kept up. So you mentioned the sort of hybrid model where you've got quantum computers and normal or ordinary computers. I'm just wondering if quantum computers are the ultimate answer for everything, or are existing computers going to be around? Give me an example where you would want to use a quantum computer on its own and where a hybrid model works. What sort of problems need to be solved with quantum?
If you've got a problem where you want to find the classification of a data set into two different categories or something like that, and there's a huge number of parameters and it's very complicated, and this is the kind of thing that a conventional computer would normally do by projecting it into a multi-dimensional space and then doing lots of minimization capabilities within an algorithm to be able to say, this is the slice through that data in a multi-dimensional space using a hyperplane that's going to divide this data set in two, and therefore you can predict in the future whether I'm looking at type A or type B of something. So that's the kind of thing that quantum computers will do, and are doing already to a degree on their own, and will do it very well, because these are ridiculously complicated, multi-dimensional, faceted problems that scale exponentially using our normal technology. So normal computers would sit there and go, to work that answer, as the problem gets bigger and bigger and bigger and bigger, the actual processing I have to do grows exponentially. So, to do one problem of size 1 takes 1, problem of size 2 takes 2, but then 4, then 8, then 16, then 32, then 64, 128, 256. The numbers get very big very quickly. And what the quantum computer does is then in many cases either turns that back on itself or reduces the time that it takes. Basically, rather than it being a problem that gets exponentially bigger, the bigger the problem gets, the problem either turns into a linear problem or an n-squared problem, which isn't as bad. It means you can crack the problem a lot faster. And that's what quantum computers are really good at. Yeah. Now, having said that, there are some things at the moment that quantum computers aren't brilliant at. It's not superb at dealing with large amounts of data, for example. So if you had to deal with an algorithm where you have to process large amounts of data against a quantum computer algorithm, what you might do is start, using the conventional computer to divide the problem down, spread that over multiple quantum runs and then assemble the problem back and then make a decision based on that result and do it again. Hybrid algorithms and hybrid ways of working are going to be around for quite a long time. And it's probably where we're first going to see quantum computers actually overtake conventional computers, is ironically actually working with classical computers to solve problems that a classical computer on its own couldn't solve, but with a helper mate of a quantum computer will be able to solve and will do so in a reasonable amount of time. So there's different ways, but I think what you'll see is quantum computers being used as an assistant, if you like, to traditional computers to deal with really big and hard problems. And that's why we're working very hard on things like that, those online interfaces and the serverless capabilities we've been talking about, because that's how you create really the next generation of supercomputers. The actual conventional chips that we all use in our computers or in our phones or everything else are beginning to hit the boundaries of what they can do cost effectively, because we're running out of atomic space. We're running out of room at the bottom, if you like. Gates on chips are getting very, very small.
When we look at things like 5G, edge computing is coming into its own. They're physically placing servers at the cell towers so that there is a very short latency and problems can be done locally. I'm just thinking aloud, you're right that my phone is reaching the physical limit. So for where you need to offload some computing power, is a quantum computer able to offload that? Here's the problem. I've processed the problem as much as I can on the device I have, off to the quantum, and back comes the answer. Is that the way it might work in hybrid, the kind of the edge computing model?
Yeah, that's exactly it. Just as you take a problem off to the cloud at the moment because you can't process it on your watch or whatever, this is the same kind of idea. You can't process it on your supercomputer, so you offload it to your quantum computer. So it's perhaps it's the next layer up, if you like, of offloading. But yeah, that's exactly it. We're going to see a really exciting time in the computer industry over the next decade or so. Almost all of my career, we've had computers that look the same, behave the same, work the same. Yeah, they've had slightly different architectures, but they're all fundamentally the same computer. Same with what's in your watch or what's in your phone, same kind of thing. Whereas I think what we're going to see in the future in their gaming PCs and this kind of thing, and used to do lots of hard work at the moment, because we've got to get more efficient at solving problems. It's not good enough anymore to just simply, as we used to say, throw more tin at it. We've got to be responsible. We've got to find efficient ways of doing really hard problems, and quantum computing is one of those ways.
So you mentioned that IBM was literally there at day zero, and you've been involved in this for a long time. As an industry, is there an opportunity for all of you to work together to perfect that quantum computing for the benefit of all?
To a large degree. I mean, I wouldn't say we're all working together, but I think we're all working to a similar goal, and we're all learning. So a lot of what IBM does, in fact, almost everything that IBM does in this field, is published, is either open source, or even things like gate fidelities and the actual gigahertz measurements of the individual qubits, and we publish all that stuff. So there is a wealth of knowledge going out into the academic and into the engineering and scientific communities from companies like IBM and others that is actually forming this, this global ecosystem, if you like, of quantum capabilities. There's technology beyond quantum computing as well. There's quantum optics and there's quantum sensors, which the UK is very strong on, for example. We're going to need to be able to link quantum computers together. We need networks. So we're going to need quantum optics to be able to do that. So there's an awful lot of academic and industry collaboration going on. There are lots of different, as I said earlier, there are different types of quantum computers too. So I think everybody's learning together, and that's why that acceleration over the last, 6 years since we put the first quantum computer on the web. I think that's been part of what's been driving this, as well as obviously huge amounts of investment, but it's what's been driving this very fast acceleration of the field. We are a long way ahead, I think, than where we thought we were going to be even a few years ago.
So I want to talk about your career for a bit, because you've had a very interesting career. Your undergraduate degree is English language and literature, quite the contrast to quantum computing. Tell us a little bit more about your journey to working in quantum from an English lit degree.
To be fair, I did do maths and physics at A-level, which is the kind of like the precursor to university in the UK, and I was pretty good at them, all right? So when I went to university, I asked my university whether I could actually do English and physics together, and they said it was all too hard and timetables and wouldn't know what degree to give me and all that kind of stuff. So basically they persuaded me out of it. But having persuaded me out of it, I am intensely curious and remain so. So I just spent quite a lot of time at university on the wrong floors of the library and educated myself in computers and everything else. So when I left university, I still didn't really know what I was going to do as a career. Was I going to be a journalist? Was I going to be a teacher? Was I going to be a computer person with IBM? And in the end, I opted for the technology route and have never regretted it. It's always been amazing. I've never stopped learning. These days, you almost need to be doing, an hour of education every day that you're working. You need to find that time somehow. 200 hours of education a year, I think, is what's required. So that kind of level of investment of time, when you secure it, is the kind of thing that to be able to branch out into these different fields and push some of the boundaries.
I use the phrase with my audiences, they want to become digitally curious and just lean forward. So one of the reasons I have these podcasts about things that are a little bit in the future is I want people to be open to this and then go, whoa, quantum, I should do some reading on that because it's going to impact our business fairly soon. So I like to be a little bit ahead of the curve as you do. But like you, I'm also passionate about talking to school-age students about careers in technology. And as a quick public service announcement, I'd recommend you to get involved with the Speakers for Schools charity run by Robert Peston and Co. I speak to students several times a year, and the one thing they ask me is, what's the jobs of the future? What job should I be studying for? You're a STEM ambassador. What does that entail? And maybe you could talk about what the future jobs that involve quantum might look like.
STEM ambassador is one of the things I adore doing. I'm also a fellow of the Royal Academy of Engineering, and that gets me involved in their bursary schemes and their scholarships and this kind of thing. So probably the highlight of my year is actually interviewing people to be able to give away money for bursaries and scholarships to, especially for those who've had difficult backgrounds and this kind of thing. So it's hugely important, I think, that people who are skilled and knowledgeable in fields like computing spend time going into schools, going into universities, going into colleges, and actually making the time to communicate what they do, why they do it, why it's exciting, and ideally showing something that actually will capture the imagination. I build robots in my spare time, so I take robots into schools. I can usually explain fairly easily what IBM is and what IBM's done over the years and why why being a technology company is cool. To explain what an engineer does or what a scientist does, is that little bit more intangible. So actually having something to show and to demonstrate that's really what I enjoy doing. It's ensuring that we bring on the next generation and making that as broad a section of people as possible. Because at the moment, when I look around my august fellows all tend to look an awful lot like me. And that's a bit depressing. So we've got to fix that.
Couple of interesting things. When I last spoke to a Speakers for School audience, I asked for a show of hands. These are sixth formers, so 16, 17, 18. I said, who'd heard of IBM? And no one had heard of IBM. That's not a criticism. They haven't heard of these companies that have been around for a long time. Of course, Google and Netflix, all the hands went up. One thing that came up a lot, I was actually mobbed by 20 students afterwards that wanted to know all about the jobs and opportunities for the future. A couple of them said, look, I'm not really that interested in deep technology. I'm more of a humanities. Are there roles for people in the quantum world where they don't have to be a boffin like you or I, a loving geek, but can use their creative side to actually help solve problems? I want to make quantum computing accessible for people that don't just think they have to study engineering.
We are doing a lot to make it as simple as it possible can be. So even right now, you could log on to the IBM quantum experience and go to the composer and actually write a quantum program without writing a line of code. You literally just go, oh, well, I'll do that and I'll do that and I'll do that. You don't have to be the deepest techie or even understand how quantum computing works or gates or anything inside it. You don't need to do that to be able to use a quantum computer. As this area grows, there's going to be people who need to know how this changes their industry. They're not going to need to have deep knowledge to do that, but to apply that, to understand how an area works or a business works or an industry works, and then understand how the two fit together. That's possibly one. We've already got musicians and artists using our software for art installations and for generating pictures and all kinds of things. And there's always going to be the need for people who can communicate this stuff. We need technical writers. We need people who can actually sell the stuff eventually. There are going to be a lot of roles out there that are associated with quantum technology and quantum computing that aren't necessarily that technical. Just in the same way that mainstream computing's got a lot of people who are relatively less technical wrapped around it these days. As it becomes more mainstream, that'll be the case.
Is there one sector that can benefit most from quantum?
It's a timescale thing. Places like material science, possibly drug companies, people who are actually involved in trying to understand that natural world down at the smallest level and understand how molecules work and how materials might have properties and this kind of thing. Those are the people who are going to benefit from quantum computing first. But then you look at other industries, like the financial industry or something like that. They've got huge problems. I mean, in terms of, how do I detect whether a transaction is fraudulent or not? How do I look at this portfolio of stocks and shares, and what do I do next to optimize it for my customer? Even bigger level, I'm running a bank. I need to ensure that it maintains liquidity, that it, so I'm looking after my risk stance. How do I model all of the movements of everything around the bank and understand all the future conditions and everything else? How can I get a more precise picture of that that's more inclusive of more factors that would then allow me to free up some cash so the bank can do some more exciting things? And it's those kind of use cases that are emerging at the moment, that they won't be real for a while. But actually, we've already got clients looking at them. Moving from the physical kind of world through to the symbolic world of banking, if you like, that's going to be the journey over the next 5 or 6 years, I think.
So I've been reading up about the IBM Quantum Network. Can you tell me more about this and who signed up to be part of it?
I think there's about 180 members of it now, and that's all the way from research institutes, startups, and household names. Goldman Sachs and Capgemini, Cleveland Clinic in healthcare, ExxonMobil in the gas industry, Samsung, Sony, Boeing, MIT, JP Morgan Chase. It's a global phenomenon of different kinds of companies, from the very small to the very big, all kind of working together in kind of hubs of industry and academia, that it has helped us make this huge progress. So it's this kind of cycle of industry, academia, and technology companies that are really accelerating the field. And, that's why we're seeing all these different potential use cases for quantum coming to light.
And that's the great thing about having an ecosystem that's open, that they want to feed things back. And like I said before, may not be working with competitors, but with clients. Hey, we've solved this problem. And then think, we hadn't thought about that. That's another way to do that. So I see that as a really healthy way of leveraging your ecosystem. Obviously, one of the companies at the forefront of quantum research. I understand IBM has a quantum roadmap, so we're able to rent time on a computer at the moment. So what's next for the IBM quantum story?
Quite exciting, actually. We published the roadmap first a couple of years ago. And first of all, the whole point of it, and we've stuck to it. So everything that was on that roadmap, we've delivered. And then we issued the new one this year, which takes us out beyond 2025. And it shows a shift in ambition. The original roadmap was all about putting more and more qubits onto a chip. What we're doing now is a multi-pronged approach. So not only are we going to add more qubits on the chips, we'll be going from hopefully 127 qubits to 433 qubits, for example, on the chip. And then next year, even more. But we're also now working on how do you link those chips together so they can form a bigger quantum computer without requiring ever more chips. Because ultimately, you've got to get, as I said before, you've got to get the information in and out of the chips. Each qubit is controlled outside of the chip. So there's probably a limit to the size of an individual chip is going to get for a while. We're working out how to stick them together. First of all, in a kind of way that we're familiar with from normal computers, in a kind of multi-processing kind of way within the same fridge. And then ultimately going outside of the fridge and linking them up via local connection buses equivalent to LANs, and then ultimately WANs, so wide area connections that will be able to join in completely different fridges together. There's quite an exciting story to be told. By the time we get to 2025, we'll be talking about 4,000 qubits or more. That's really only the start, because that 4,000 thing is based on the idea that we've now got a modular technology that we can start building bigger and bigger machines on. We think it gives the roadmap to get to a lot bigger than that. It's really putting those fundamental building blocks in place to get us away from just being in a single chip that's doing all the work to how do you get many chips to work together and many fridges to work together.
So one thing we haven't talked about, but probably one of the most amazing technologies, is artificial intelligence, or AI. Now, AI needs a lot of computing power. So talk to me about where AI and quantum can work together, and does that supercharge AI? And does that mean we're going to get to artificial general intelligence a bit sooner?
Well, that is a good question. People may not know this, but the actual amount of energy we expend as a planet on artificial intelligence and machine learning is currently doubling every 3.5 months. That's one heck of an exponential curve. We have a problem. Quantum computing is one of those ways we should be able to tackle some of those workloads, maybe not all of them. We're not going to take a 175 billion parameter model like GPT-3 and suddenly turn it into a quantum algorithm. But for certain types of tasks and certain types of optimization and classification tasks, then I think quantum will be a way of taking some of that workload and doing it in a much more efficient kind of way. There's every possibility that quantum computing will find areas where it can accelerate machine learning, and will, I'm sure. And will that contribute to AGI? That's a really hard one. Big topic. Quantum has that ability perhaps to sit alongside large natural language models and symbolic models and quantum models, and they can all work together. And that's kind of what we're building, is that ability for things to work together. So maybe that will accelerate AGI. I don't know, but as no one knows how to build one yet, it's a bit of a tricky question.
I thought I'd sneak that in there because I've spoken to a few experts on the podcast about AGI. At the end of every podcast, I ask people who should be next on the show, and maybe you can suggest someone who's an AGI fellow, but we'll talk about that in a moment. I've now got another study in my brain about AI and machine learning, how much energy it consumes, and that's a real problem for the planet, and that's something I hadn't been aware of. Quantum's going to help with efficiency. But let's look at maybe some bad ways that quantum can be used. Is there a risk that quantum computing is so powerful it could be used by bad actors to, for example, break cryptography that's used to secure networks and platforms today? What can be done to ensure that this powerful form of computing doesn't fall into the wrong hands, or we stay ahead of the bad guys and gals?
And that is a genuine possibility and problem. As I've talked about, it's not so much like building a single computer that can do this if you can string them all together, and how fast you get to a quantum computer that's big enough, we still don't know. It's quite a way off, given that we're talking about a 400 qubit chip this year. If you've got data that is intrinsically valuable in, say, 20, 30 years' time, what happens if that gets stolen now using today's cryptography? Because someone in 20 or 30 years' time might be able to, who knows, might be able to decrypt it. And that would be a bad thing. And there are some organisations around the world that do care about that level of cryptography that far out in advance. So we've been working for years with NIST, which is the standards body over the States, and others to actually establish new cryptographic frameworks that we think, and we're pretty certain, are not crackable by quantum algorithms or by quantum computers or by conventional computers for that matter either. Our current batch of mainframes that we just announced, that the banks used to do all their big processing and everything else, they have got quantum safe algorithms built into them now. So making it much easier for the big institutions of the world to move across. And I think the other thing we'll see as things go forward is this desire and need and requirement to be cryptographically agile. At the moment, cryptography is almost baked into things. Changing it is one of the hardest things you can do. Re-engineering a telecoms network is a difficult thing to do. Re-engineering the cryptography of a large bank is a difficult thing to do. I think what we're going to see is technology coming through that's going to make it easier to switch cryptographic regimes and algorithms. That'll be less of a problem in the future because we'll have made people more cryptographically agile and they can move schemes more easily. Even if this does get into the hands of bad people, and every technology can be misused in some way, shape or form, that actually we can mitigate those risks, both now, but also way into the future.
Cryptographically agile.
It just trips off the tongue, doesn't it?
I'm now seeing VPN companies that are saying we have a quantum-proof algorithm, and I always think about that when people say we can't be hacked, you need to be careful what you wish for. But being agile, I think you're right. If you think about your door lock, here in the UK there's a company called Banham, and if you have a Banham lock and you lose the key, it's deliberately very hard to replace that. We're almost out of time, but what are you most excited about when it comes to quantum computing?
It's the real-world impact that really gets me going, especially in some of those early areas around material science, batteries, that kind of thing. The world spends about 1.5% of its gas supply on fixating nitrogen, methane turning into fertilizers, basically, using a very expensive process that works at hundreds of atmospheres and hundreds of degrees Celsius and isn't actually that efficient either. And the process, although it's been refined, is fundamentally the same process that was invented back in the early 1900s, which is how in the 20th century we managed to get from 1.6 billion people on the planet to 6.1 billion people on the planet. We invented artificial fertilizer, and that allowed the population to massively grow without starvation. But that's a huge energy cost. Is there any other way of fixating nitrogen? Well, actually, You kind of look around and you see plants, and they're kind of doing it already, which is interesting. So if you could get the enzyme, nitrogenase from plants, and turn that into a catalyst, then you could potentially save an awful lot of energy and reduce the environmental impact of feeding lots of people. And interestingly, the number of atoms in that molecule, in that enzyme, isn't that large, and possibly is amenable, in the relatively near term, to being modelled by quantum computers. It's those kind of things that excite me. If you could lop off 1.5% of the world's gas consumption in one go, and that's one example. How many other examples are out there? Are there ways of doing carbon capture that are efficient using new materials? It's that kind of stuff that I think is going to make the real difference to the world. Improving batteries so that we can store solar and wind power for when we need it. That whole molecular engineering, materials, I really, really, really hope that actually quantum computing will be real enough to enable us to do that and to make a real impact on the world.
So maybe quantum computing is the future. You heard it here, folks, first on the Actionable Futurist podcast.
Well, you got to hope.
So we're now at my favourite part of the show. Before we finish, I want to run you through a quick fire round so we learn a bit more about the person behind the mic. iPhone or Android?
Oh, iPhone.
Window or aisle?
Oh, window.
Online or in the room?
Oh, online.
What's your biggest hope for 2022 and beyond?
I'd love to see quantum advantage. I'd like to see that done in a convincing and amazing manner that just wows the world. I'd love to see that.
What's the app you use most on your phone?
Sadly, it's Slack, because lots of people want to talk to me.
What's one thing you won't be doing again post-pandemic?
I won't believe any model until I've inspected the code.
That's probably the most scientific answer I've had in the last 4 years, but thank you for that. What's the best piece of advice you've ever received?
The Eisenhower Matrix. Use the Eisenhower Matrix.
What are you reading at the moment?
A Doctor Who book called Wolfsbane. I'm reading Thinking Fast and Slow by Daniel Kahneman. And I'm also, because my daughter just bought her first house, I'm reading up on Japanese courtyard gardens with Haruzo Ohashi.
I'll put links to all those books in the show notes. People will be always thrilled to understand what our guests are reading. So I alluded to this before, so you've had a bit of time to think about it. Who should I invite next onto the podcast?
Lucy Rogers. Professor Lucy Rogers is a bit of a star. She's also into robots, but she's also written books on rocket science and everything else. So I know it's not in the AGI area that you wanted. She'll be a great guest.
Final quick-fire question. How do you want to be remembered?
I'd like to be remembered as a good dad.
So as this is the Actionable Futurist podcast, can you give me 3 actionable things our audience should do today when it comes to better understanding the promise of quantum computing?
3 things they should do. Well, first of all, they should log on to the IBM Quantum website. Get yourself an ID on that. Task number 2, read the first chapter of our quantum textbook, which we'll find there, which will actually teach you what the basics of the gates are and will give you an idea of how quantum computers work at a level we haven't got onto on this podcast. And then the third thing is, given what I've said, think about how quantum computing might change the world for them and in their domain and in their sphere. I think if they did those 3 things, that would be a good use of time.
3 very actionable tips. I like those. I can do them myself. Richard, how can people find out more about you and your work?
If you want to find out about me and quantum computing and everything else, then search for Richard Hopkins IBM. That'll find me. If you want to know about my robots and my STEM work, search for Richard Hopkins K9. And then if you want to get in touch or ask questions, if you search for Richard Hopkins on Twitter, I'm the one with FRENG, French, after their name, so it's easy to spot me on Twitter as well. So I'd love a connection on Twitter if anybody wants to have a chat.
Richard, as I expected, I've learnt so much today about a subject that's fascinating. Thank you so much for your time. I really enjoyed talking with you.
Andrew, pleasure talking to you too.
Thank you for listening to the Actionable Futurist podcast. You can find all of our previous shows at actionablefuturist.com. And if you like what you've heard on the show, please consider subscribing via your favourite podcast app so you never miss an episode. You can find out more about Andrew and how he helps corporates navigate a disruptive digital world with keynote speeches and C-suite workshops delivered in person or virtually at actionablefuturist.com. Until next time, this has been the Actionable Futurist Podcast.